Hey YouTube, Bil Herd and Ben Jordan coming at you. How you doing, Ben?
Good to see you, Bill. Very good.
We're always a minute late because right as I go to do this, YouTube says, "Oh, you have to re-authenticate." Or I'm sorry, my broadcast software has to re-authenticate, and I can't test that until we go live. And then it says, "Aha, here's a curveball." So, but we're here. We made it.
We made it. I just wanted to note that I can see the live stream. And I hit mute, but I did see you talking before I hit mute, but I didn't hear it. However, I think that's just because it's going to my other audio interface. So I believe we're good with sound, right? Nothing
Okay,
else.
yeah, I hear you. I hear you good. Everybody on chat, do we sound okay today?
Yeah, I know. It's my YouTube channel's routed to the audio interface that's
Right.
got my mic
Okay.
input on it. So I
Very
think
good.
We're good. We're good to go. This is great.
So, very cool. Yeah, we got a lot of things to talk, a lot of little things, not like the big thing where we threw NTSC at everybody and said, "Hey, NTSC." Yeah, we're saying sounds good from John. Yep.
Cool. Awesome.
So, hey, so I saw something when we were talking about NTSC, which had me befuddled for a second. And actually, Alan Wolke said, "Hey, hit single trigger," and we did a single trigger of the color burst, and then you could see it clearly. But I was scratching my mind. I'm going, why is the phase shifting? If I'm looking at line 21 of every single frame, odd frame, for example, why is there superimposed 180 degrees out of phase, two phases of color burst? So I asked Kerry Sagety, the very man I was talking to that did the NTSC camera and did the Genlock for the Amiga. I said, "Kerry, my brain is fried. I can't remember." And he's like, "Absolutely. It's every fourth frame it'll repeat." So what's happening is because of the NTSC spec, they invert the, even though it's not PAL, which is phase alternating line, that's slightly different mechanism how we do it. But it inverts the color subcarrier from line to line. But my old analog scope, I didn't have to do too much special to do it. And I got curious as why on the new scope can't I get this display like you see here? And here it's doing it now because I did figure out what to do. And I wanted to show that to everybody. See this color burst right here, how it goes up a little bit, then down, then up. And we are on... let me see if I can find the trigger menu.
Hey, do you want to make that full screen so people can see?
Okay, yeah, I can do that. Now I have to run over to the scope itself here. So what I'm going to do is bring up the trigger menu.
It's still kind of hard to see. There's a few things.
Yeah, I see that. Myself. So let me. Right. Apologize, everybody. So what I'm doing is triggering on a line number. And there you can see I'm triggering on line 23, but I have a hold off. And this is what's really cool. Hopefully you can hear me. Is I have a hold off of 2.5 odd frames, which means that I just met that criteria. So where it repeats every 4 times. So there's odd fields, which is every other frame, and then every other one of those, the phase will be the same right here. So to prove that, what I'm going to do is I'm going to change the line number. Let's see if I can do this.
And we'll see it go down first.
We should see it invert phase. So we're going to go from 23 to 24, 23 to 22.
Yeah.
And we see that the phase is inverting.
It's
now,
very clear. Yeah.
Right. And so the way I got that was my digital scope has this nice mode called where I can hold off a field. Hang on, now I'm trying to. But I had Mike Fikes then, who has an old he's got a 465 with the TV trigger built in. And I said, "Mike, get yourself an NTSC generator. He did already during the week, same one. He hooks it up, and I said, Mike, now how in the old days was I getting this stable thing? And he found out that he read the manual, and what it is there is a hold off in microseconds. So whereas I'm able in a digital world to hold off by a number of frames, what we did in the old days, we were holding off by a number of microseconds. And I asked Carrie, I said, what's up? Why are we inverting the phase? I love the answer. And that was part of, they changed the spec. Remember I said it's not 60 hertz for a vertical frame anymore. It's 59.94. They squeezed everything so that the phase of the color burst would flip back and forth between 0 and 180, and that's for noise reduction techniques. So independent of phase alternating line, they changed. They had so much trouble with early NTSC with artifacts. For example, the horizontal frequency is divisible is related to the difference between the audio subcarrier and the color subcarrier. They would beat against each other, create an intermodulation, and so they changed the sync pulses to minimize the movement of that intermodulation on the screen. I mean, they're inventing this. Oh, it is. It's madness. So then, guess who I got to talk to yesterday on the air? And Ben, you know this.
Oh, yeah.
If
anyone was on our Discord channel and following and paying attention, you'd have seen there was a really cool event yesterday where Bill got to speak, and it was a collection of some pretty amazing people talking about the 6502 and its origins, including the granddaddy of the 6502 himself, Bill Mensch, was there.
Right.
Had a lot of interesting stories to tell, and others. But Bill.
Yeah, so the really cool session was the second hour session where instead of breaking out, we all stayed in one room. So I got to talk with Bill Mensch live with everybody else, and Al Charpentier, the creator of the VIC chip, who is he is right up there in my mind with Bill Mensch, because what he made in the VIC chip for the Commodore 64. Let's say, yeah, I'd still call him equal with the work Mensch and those guys did. Yeah, it's genius work once you hit that genius level. And so we were chittering about the NTSC of the day, and guess what he talked about? He talked about that phase lock loop that we did in the Commodore 64 schematic reveal. So I've sent him that leak where he's talking about, oh yeah, we fired it up and we get this moire pattern and we had to phase lock it. And I'm like, I just did a video on the phase lock, and I'm sitting there guessing that you had to do this and that. And so I got to talk with one of the really cool people that made the Commodore 64 available. The rest of the show, there was a lot of talk about Apple One, and I loved what Al did, though. He said, if you look in the Guinness Book of World Records, however, it says 27 million Commodore 64 sold. So it was like, yes, somebody in my own camp, right? Because there's still a lot of Apple people out there. Nothing against you guys, but...
You know what that should mean, though? That should mean that there are 27 million of them out there somewhere, and they should be accessible. But I wonder how many of them actually eventually wound up in e-waste recycling or landfill.
26.9 million. Yeah. Now, with that said, that's what the Guinness Book of World Records said. It's possible there were less actually sold, but that's for a different show. So.
What, you mean someone lied?
Well, they got the Guinness Book of World Records. What great advertisement, right?
Yeah.
Right?
Totally.
So that was my thing yesterday, is I got to be part of the World Computer Day and got to be in a forum with Al Charpentier and Bill Mensch, as he likes to be called, the mother of the 6502, because we typically call Chuck Peddle the father. And Chuck comes from a systems background. And he got a team, like a great mask cutter, a great systems guy, great InMOS designer in Bill Mensch. And so it was the team that made the 6502. And so he likes to be known as the mother of the 6502. And I've said that about the 128. I call Fred Bowen the father of the 128 because he was on it before I was. And I came along as a hardware guy, and I became the mother of the 128. So mother to mother, we have that connection. So it's all cool.
That's cool.
So hi, Mondo.
It's been a busy, radical week. With a lot going on.
Yes. So anyways, there was that little NTSC. Thanks to Mike Fikes for verifying how I was able to do it on the old analog scopes before I had the ability to do a hold off of 2.5 frames, which is just awesome.
And verifying the 4.8% THD of the sine wave tone output of that same NTSC test generator. I guess the point was that the sound comes through and is decoded correctly.
Demodulated. Yeah, it's
it wasn't meant as an audio analyzer or anything, but 4.8%, and it still looks like a pretty decent sine wave, although it's a little more triangular than sine, let's say.
Right. Right. Which means there's harmonics in it, right?
That's right. I think even the current cheap generation, like I got one of those maybe 2 years ago. I bought the FieldTech $80 or $86 DDS function generator off AliExpress. We've seen a lot of reviews on those across YouTube, including Dave Jones did one. It's actually a pretty awesome little signal generator for $86. Unbelievable, actually, how good it is. And I can say that.
Which generator is that?
It's let me switch and I'll show you.
Okay. Oh, I know what you're talking about. Yeah. Show us that.
So this is the bench. That's the sine wave output from it at 10 kilohertz. It's a pretty good sine wave. I know we're not up close. Oh, wait. I didn't switch.
Yeah, we're still on the camera view. There we go.
Me out on that.
Yeah.
It's actually, let me move the camera up. It's this one here. This little FieldTech, just a plastic case, got its own switching power supply built in, but it does have USB. It comes with a National Instruments driver and an app that's kind of difficult to install because all the documentation's in Chinese, but it does work. So you can control it by a PC. 2 channels, does modulation, AM, PM, and FSK with an input. 250 megasamples a second, 14-bit DAC. So it's pretty good. It's not going to be audio grade with 14 bits. You need at least really 18 or ideally 24-bit DAC for low distortion audio.
Right.
For test.
How low of distortion does the sine wave generator? We were talking about an audio distortion analyzer last week. How low a distortion do those have to be before they're usable in a THD meter? Total harmonic distortion.
Vanishingly.
They like 0.001, something like that.
Probably 3 zeros and a 1.
Okay. Most. Wow.
And that's why audio analyzers are so darned expensive. They have a lot of stuff in there. And I did download the service manual, which explains how they do it during the week, and had a quick look at that. So maybe we could look at that later. But this is my test setup for this new instrument I got, which I mentioned last week. I got this at the San Diego State University. UCSD, University of California, San Diego, has a big facility here in Miramar. It's just a big warehouse where they auction off and sell off cheaply lots of old stuff, furniture.
Right.
I got a bunch of office furniture from there too because it was
cool.
pretty decent and cheap. I got a couch, coffee table. But occasionally you'll find a gem like this. This is a true RMS voltmeter. There were 2 versions, the 400 and the 400E. The 400, I think, just shows volts, and the 400E, the only difference between them, from what I can tell, is the scale on the meter. The 400E has dBV.
Okay.
With reference, so 0 dB is full scale, 0 dB is 1 volt RMS.
Right.
But there's scaling. There's voltage range scaling here. So, so depending on the scale, full scale at 0 dB. So I have dB scales on this side, so I can switch over to here and read the top of the meter, and actual volts on this side, and I can go. So this goes from ranges from minus 60 dB all the way up to plus 50, which would mean at full scale on the dB meter, 0 means plus 50, which is 300 volts RMS. 300 volts RMS if you're dealing with one sine wave. Like if it's DC, that's 300 volts DC. But if you're dealing with a sine wave, 300 volts RMS is it's close to 800 volts peak to peak.
Right. Right.
So this thing has pretty decent input. I haven't tested all the ranges. I will get around to that. I don't have a suitable source for 300 volts RMS hanging around right now. So
other than the 240 volt source.
Well, I'm not gonna. Yeah, I don't want to do that. But the key is this True RMS voltmeter. One of the things that makes it so special is that it supports True RMS all the way up to 100 megahertz, I believe.
Yeah, that's amazing.
That's ridiculous.
For the day, yes.
Ridiculous. And if I look at, let's do, so it appears to be working. I just have a 5 volts peak to peak sine wave at 10 kilohertz. And on the scope's doing its math. It says RMS 1.76 volts RMS. The True RMS meter appears to be showing the needle in a location that sounds quite reasonable. This has probably never been calibrated officially because it doesn't have, well, there is a sticker on the back, but that's just a serial number. So I don't think this has been used in a university sort of lab environment. I don't think it's ever been calibrated, but I could be wrong. Maybe that's what this label, which I want to get off, although this is probably an asset tracking ID from the university. Anyway, I won't pull that off now. Obviously, with anything like this, parts are old, and you know, I could jiggle this around. You can see the needle jumps around a little bit. I think the contacts need some joy juice in the rotary switch.
Right.
But appears to be working fine. I haven't cleaned anything yet. Haven't taken it apart. I have the sides and top on these are, I think they're aluminium, but they're vinyl coated, and the vinyl after so many years is a bit sticky and gross. So I've actually scrubbed that with some paper towels and isopropyl alcohol. I'll probably go and do the contacts here with isopropyl as well. But I'm happy with this. It looks like it's working. And the cool thing about these, they also have a couple of neat features. That they have binding posts on the back, so you can hook up plus and minus battery supplies, so you can have it completely isolated. They would have done that because back when these were released as a new product, the main audience would have been anyone doing RF, and particularly if you're talking about 300 volts, you're probably talking about power transmitters, RF power transmitters, where you're wanting to measure the voltage going to an antenna or some kind of RF matching circuit or something like that. Again, up to 100 megahertz, so it's not microwaves or anything crazy, but super, super useful. And it has an output, an AC and a DC output on the back. So it gives out DC that's exactly proportional to where the needle is. And it gives out
That's
a repeated AC signal. And I haven't looked at that yet, but if we look at the service manual, so I've got the...
So it's a precision rectifier.
Basically, yeah. So what I want to do is I'll share screen and we'll look at the... Let me know if you can see this start sharing.
Okay, I see the blue S.
Right?
Just the blue S. Hang on, let me see if I got a share screen. Are you doing it from a camera input or share screen?
No, it's just from Skype, from share screen.
Okay, let me find that. Hang on.
Let's go to full screen mode. You're seeing it?
Yep, I'm pulling it out so it's on top. Yeah, here we go.
I want to wait. I want to go wide here so we can look at everything. Let's go page display 2 up and then full screen.
So they're telling me in the chat I need to WD-40 my chair, that my squeaking has got a dog on hide. Yeah, I didn't realize that, so I'll deal with that. I could throw a high-pass filter on that, but...
This, for such a supposedly simple device, it just measures voltage. That's it. There's a lot of bookmarks and a lot of pages to this operating and service manual. So
right. Well, and they probably show you how to repair it, right?
They do. Yeah, do not service and adjust alone. Yes, this is dangerous.
It's in other words.
I'm sorry. I was incorrect about 100 megahertz. It's 10 megahertz. So it's not quite as neat as I'd thought, but still 10 megahertz is
10 megahertz, right? Right.
It's good for a radio ham. Yeah, so the AC output, so it gives 150 millivolts RMS for full scale meter. So what's
its impedance?
Let's see. And 1 volt DC for full
there it is,
meter.
10 mega ohms. It's right above you by 2. 10 mega ohms shunted by less than 25 puff.
Yeah.
You can tell I'm an old timer. I say puff.
That would be the main limiting for frequency, along with other parts of the circuit, of course. But
right.
So this is a really neat meter, and I'm going to enjoy cleaning it up and getting it in pristine condition. So
yeah, there's advice in the chat about how to do some degreasing and stuff on it. And then there's things like goo. You have to be careful, obviously. And do test samples on your stuff.
That's right.
Goo Gone is still useful. Isopropyl alcohol is my go-to usually.
I love Goo Gone, or it's orange oil, right? The problem with orange oil is it will attack plastics as well. So
and even IPA will do that too.
You can get the goo off, but you have to thoroughly rinse it afterwards. Whereas isopropyl will mostly just completely evaporate away as soon as you're done. So, but yeah, I use Goo Gone to get rid of label goo, or sometimes WD-40 does the trick as well.
Right.
But yeah, I'll go back and check the chat. If anyone has any better specific things for PVC that's gotten sticky over the years because it's weeping the plasticizer oils.
Right.
If anyone knows a better thing than that, I'll give that a try. I'll check the chat later for that. So, yeah.
Very cool.
It's cool. Look, the ranges are limited beyond 4 megahertz. I'm seeing as well. Oh, these are this is the outputs, the DC, AC to DC converter output. So yeah, I mean, and it's got some very big warnings about applying high voltages when it's on a low voltage range to not do that. It can damage the unit.
Oh, okay.
So there's
Right.
a rule here. If you're going to apply 500 volts AC, the meter, they're saying only allow up to 500 volts below 1 kilohertz. If I'm dealing with, so the higher the frequency, the lower the voltage I should be allowed to apply.
Right. Right.
Yeah. So, yeah. Anyway, there's just the descriptions of all the stuff. What we want to do is get to the schematics. They're explaining how it operates. So this is really cool. So we have the input range attenuator, an impedance converter. I'm gonna move that little Skype preview.
Yeah, I was gonna say, yeah, now it's in the middle of the words, unfortunately.
I don't know. What
Stick
do you
it top left
word?
corner. Top left corner.
There.
There you go. Yeah, that looks good.
Yeah, so we go through an impedance converter, post attenuation, meter amplifier, obviously some tuning parts in there, and a meter bridge to drive the meter, and then a buffer to take the meter amplifier output as the AC output.
So the impedance converter is really the high impedance source that creates a low impedance drive internally, right?
Yeah, I'd say it's basically a buffer, and that's how
Right.
they've drawn it. It's like a non-inverting amplifier with zero gain, like straight up negative feedback to make the gain equal to 1 or 0 dB gain. So here's
And then the
it's
next stage
interesting,
shows.
and this
Go
is
ahead.
where perhaps some people in the chat could chime in too. They're describing how the meter amplifier works on 2 different half cycles to basically convert the AC input into a RMS DC equivalent.
Wow. Wow.
Let's have a look. That's operating instructions. I hate it when it keeps changing page so suddenly.
Right.
Where we installation, operating instructions. Oh, okay, I jumped back too far. That's what the problem was. So the meter amplifier amplifies its input signal by a fixed gain on all ranges except the 001 volt range. Amplifier itself is a 4-stage DC coupled amplifier with a cascade coupled final stage. DC.
And a cascade stage is what? Cascade coupled.
That mean that there's different types of cascade. So we'll see that when we look at the schematic. It could be cascode.
Cascode's the one I'm familiar. Yeah.
Yeah, and that may be what they needed, because the cascode was used where you need very large bandwidth, whereas coupled emitter follower stages or coupled common emitter stages you lose bandwidth because of the Miller effect. Yeah. But the meter bridge, and there's a description of it here, which I haven't read this, but I should, but it's more fun just to talk about it live. Bridge is something that I didn't quite understand. I know meter bridges in general, where you have a bridge of resistors, and one of them is the device under test, and you have a meter between the center points, and you have 3 other precision parts. One of them is adjustable, and you adjust it until the meter is balanced, and that's how you detect with precision the value of the device under test. for example.
And by returning it to a null, we eliminate a lot of the nonlinearities downstream of that by virtue that we're always measuring the same voltage, but because you adjusted it to be a null voltage.
Yeah. Whereas
is my understanding.
Right. Whereas in this device, and they've got the whole frequency.
Oh, cool.
They've got the whole test set up for calibrating it and everything. With
right.
Other HP instruments, of course, like DC
is the
null voltmeter.
Null voltmeter, is that
like,
just basically a bridge amplifier then, right?
Yes, and that's using that theory where you adjust the reference until you null it out, and that gives you the position, right? So let's jump to the schematic. There's all these different internal adjustment locations, where to set them. And this is a test card where you can actually go through all of these measurements and type in, enter in the results. So there's a lot involved to calibrating these. This is why any instrument calibration costs hundreds of dollars, just because it takes a long time and other specialized equipment. The disassembly notes on the rotary switch, the range switch, component locations on the board, and then they'll come to the, why did that flash so suddenly? They'll come to the schematic in just a sec. Here it is. Why is that so small? So here's the schematic. 3 PCBs, it looks like 3 PCBs. And there's 2 different options for different part numbers there. So here's our input attenuator. This is relay controlled. That's another thing that can go in these old instruments where you have relays. Those relays may be hard to get or replace if they get dirty contacts, or if someone's abused the instrument and there's been arcing. That could be a problem. Comes in through a fuse. Looks like some protection here.
Clamping. Yep.
Zeners. Okay, and again, all these things almost always use FETs, which are really hard to get. This is a P-channel JFET. So that's how you get super high impedance. I guess today in a modern instrument, they would use MOSFETs, which have even higher impedance.
Right.
Probably a depletion mode MOSFET would do the job. But back then, and even into the 90s, N-channel and P-channel JFETs that were low noise were an ideal choice for some of these applications. So you need super high input impedance. You don't want a BJT transistor, you want a FET. So this is, I guess that's an inverting, that's the drain.
That'd be a follower.
To me, that looks like it's configured as a source follower, even though they've identified that pin as the drain. But then that goes to a negative voltage.
A negative voltage.
My brain was tricking me because the voltage supply is upside down. So it is.
Right.
That is just a high impedance buffer, nothing more. No, it's an
inverter, right?
Me, but it's probably an inverter. Yeah, an inverter. It probably has some gain. Then we have another inverting amplifier and another
and see what they did there? They did the negative voltage at the top again. So that's the standard back then for them to do that.
Schematic neat and tidy, nothing more.
Right.
But in that case, to me, this looks like a buffer. But this is a feedback. I would have drawn this very differently. These are like 2 transistor stage with feedback, 2 transistor stage with feedback coupled directly to each other. I see this a lot in some of the old audio gear as well, but the way it's drawn, it looks more like a typical op-amp schematic. Yes, power supply and voltage.
The old-fashioned power supplies.
Well,
Yeah.
they didn't have 3-terminal regulators, I guess,
Right.
when this was designed. So they had to do it with Zeners and series pass device. And
Yeah.
this is your error amplifier transistor right here that's comparing the Zener to the output.
And their Q1 is a common base.
This is dual tracking. So there's only one reference, one Zener. And you can do the same thing with it. If you had a 3-terminal regulator here, you can have an op-amp driving a pass device for your negative supply, and it can reference the positive supply with regards to ground on the op-amp inputs to drive the series pass device for the negative. It's just called a tracking power supply. So whatever voltage is here, we get pretty much instant reflection of it here.
Right.
And then here's our
You see they had the shorting wires right behind there so you can measure the current right in front of TP1 and TP2. Yeah, they don't make stuff like that these days.
No, they don't.
Dave Jones just talked about that, about how you got these manuals like you're showing us on the old equipment.
Yeah, well, these were expensive instruments, and they had to make, the manual was, okay, you've got this, now it's yours, you own it, you service it, you keep it in good shape, if you have all the right equipment in your lab, you can even do all your calibration yourself. Because it's a necessary lab skill to be able to make sure your own instruments that you're relying on daily stay calibrated. And now, with most of the instruments are digital, and there's just a few things on the input which are really expensive and top secret. So yeah, it's kind of a shame we don't get a lot of this anymore.
Now, do you think you'll be able to calibrate it yourself or check calibration?
I can test it and know if I'm confident in its results, but I have no access to calibration quality instruments to adjust it and compare it with. I've got no access to references. What you need is stable references. I used to work for a power supply company when I was in college in 1993, and called Statronix Power Supplies. They made medical power supplies with a 5-year warranty, and they also made power supplies for controlling truck lighting on outback road trains that had to withstand ridiculous heat and vibration.
Right.
And the one other product they made that was a crazy, obscure thing was international voltage standards. And
wow.
These devices were like a rack unit wide, 3 rack units high, and they had a built-in oven, and they had precision wire wound resistors of different ranges that were all kept in they had Peltier elements that would heat and cool them and keep them at a fixed temperature. And these things sold for many tens of thousands of dollars to labs for the purposes of calibrating voltmeters. They were selling them into Asia for companies making handheld multimeters and all sorts of things.
And it's here in the States that we used to have the bureaus of weights and measures. I don't know if they're still around. We used to. I worked at a digital scale company, and we had a master set of weights in a room that was closed off, that was traceable back to nowadays. I don't know if it's NIST or whatnot who manages those standards.
Yeah. So that stuff, it's simple stuff, but it's ultra expensive.
Right. Well, doesn't the voltage standards, my memory is they relate back to the Josephine, I can't even say it, junction. I'll have to research that for the next show. The voltage standard comes back to, I want to say, I'm going to stop talking there and I'll research it for next show.
I think it's probably somehow related as well to...
a Coulomb.
Exactly.
Yeah, I was going to say, one of those is specified, and from there, everything else can be derived.
Right. Okay,
So I'm sitting there trying not to squeak my chair. My apologies.
So I guess what we have next is just a bunch more of amplifier stages
All right.
for the meter and some, what is this one? Range switch. Oh, that's part of the range switch. And this schematic has been edited. It looks like they took out components. Someone drew a line straight over that. So there's a couple of spaces, and I'll have to compare this to the actual circuit boards inside the meter to see if that CR19 is in mine or if it's been removed. But there's a few edits like that to this, which I find kind of strange. So these are just basic transistor inverting amplifier stages that are direct coupled. There's some feedback coming through here. That's probably for frequency compensation and limitation. See, that's a very low valued capacitor. Some more frequency compensation here and here and here. And then we get to this is a cascaded via the cascode. So we have a the last voltage amplifier stage going into a common base amplifier. The common base amplifier gives you high current gain.
It gives you an inverter. Oh, wait.
This is a common base amplifier stage.
Right.
So it gives you, so here we get voltage, and here we get, with the emitter, wiggle the emitter to control the output. The common base gives us a low output impedance, which you need for driving something like a meter. So this meter bridge here is really just a rectifier. So we have two half-wave rectifiers with our smoothing caps for positive and negative half cycles. What I don't quite understand is the purpose of this transistor in the meter bridge. And that's what I was going to ask today. And I'm sure Mike Fikes, or there's someone who's had more time lately with the intimate details of instruments, would be able to explain that. And it's probably really obvious, but I just haven't really, I'm like, here we have half a wave rectified driving the meter. The other side of the meter goes to ground through a 100 ohm adjustment for calibration. And we have absolute relative reference option. Okay.
Yeah.
But
somebody asked where the primary. Let's see if I can. I'm having trouble. Somebody said that you know what? Let me try and find it. I'm reading back through the comments here. Hang on a second.
So what this looks like to me is if this transistor, which is an emitter follower, if the voltage on the base of that transistor goes up, say, it can also feed power from our main 26 volt supply in that 100 ohm resistor, and then through its 1 k ohm emitter resistor, it can feed a positive voltage onto this cap and charge this cap. But then where does that go? I think what this means is this gives some kind of loading, because the positive voltage on C36 here will feed into this this common base stage, or to this negative 26 supply.
Yeah, can you scroll to the right? Can we see what's to the right of that bridge?
Just the meter itself.
Okay. Okay, yeah, that wasn't clear to me. Yeah. Okay.
Right, so what this looks like to me is some kind of feeding back of the meter bridge output voltage through, again, smoothing cap, it's like it's keeping this cap charged as well, so that on negative half cycles, current can flow through CR16 back through the common base stage to the negative supply. And so it forms some sort of part of the regulation of negative and positive half cycles. Now, I'll need to go back. The manual does explain how it works. I'm just wanting to look at it today and see if anyone else has seen this before and what it means to anyone else who might be viewing. But wait, this is also part of the signal chain. So this doesn't go to 0. The actual smoothing cap is C37. So that's the low pass filter. And C37 provides the ripple current needed to keep the meter steady. So again, these caps have some other purpose associated with both getting the AC output from the meter. That kind of explains more of why this emitter follower is here too.
Yeah. And there's also frequency compensation right dead center at low where it says 10 megahertz adjustment and then 400 hertz adjustment. And there's somebody just mentioned temperature compensation is probably in here somewhere.
Probably. And what was that? That's 0 volt. That's a 0 volt bias for the AC output. That's an adjustment. Then what's this? 1 millivolt, 400 hertz. Yeah, saw that. 10 megahertz. That's a. And this is interesting too. This is the other spot I'd noticed where someone has edited this schematic and drawn hard lines from our meter amplifier. To me, this looks like it just goes to ground, but I think there used to be a resistor there and ground, and this offered some feedback through the emitter of that first stage. And then to me, now it's more, these adjustments will possibly affect the meter, because if that goes to ground, there's another range switch setting. Yeah, so I don't know. This to really understand this, I'd have to convert all of these to impedances and then examine what they do at different frequencies in the current circuit. So it seems to me this is where we get our AC output from the meter bridge. And this emitter follower is some kind of buffer that buffers through both half cycles.
Right.
So, I don't know.
Very cool.
I'm sure if Alan was on the chat, he'd probably, I didn't see on YouTube, Bill, if you were looking there, he probably knows exactly what it's for and has seen it a million times.
There we go. Now I can see the meter. The actual meter movement part.
Yeah, right here.
Wow, so that voltage goes right to that jack on the back, so you could ruin your meter from the back jacks on the meter, it looks like, if
Right,
you were to apply a voltage to those.
This could be bidirectional, and that would be a problem.
Yeah. You could get shocked from it. No, never mind. Dumb
Probably
thought.
not. Yeah.
No, I forgot where we were in the schematic. Yeah.
Yeah, so.
And there is a 50 ohm output. That's interesting.
Yeah, this is our AC meter bridge output. So this gives a scaled replica of the AC signal from the meter amplifier. That gives a fixed amount of peak-to-peak voltage that is directly proportional to the RMS voltage displayed on the meter.
Right. So I guess when I was thinking earlier, could you verify the calibration? I was kind of thinking if you had a good DC meter, because to me DC meters are more accurate than AC meters unless you have an accurate AC meter.
Right.
I was wondering to what instance would is that a DC output or I guess it's an AC output? I thought it was a DC output.
DC output and an
Right.
AC output, and you know what? Let me grab my multimeter. And where the hell did I put it? Give me 1 second.
Yeah,
I'm gonna
sure thing.
I'm gonna stop sharing the screen now, and go back to Skype, and I'll go grab one of my handheld. Well, actually, I have the. I don't have it plugged in to power. I've got a Fluke 8010A up there I could use, but I'll get my tricky dick meter.
So while Ben's doing that, let me show something. Last week, I showed a spectrum analyzer from the NTSC generator, and there's something that you should know about test equipment, and you know, sensitive test equipment that acts like receivers, such as VNAs, spectrum analyzers. They're sensitive enough to catch signals off the air, right? So they're sensitive, and you have to guard their input. They have a maximum input, like 20 dBm or something, millivolt. So the very first thing I did before I hooked up my spectrum analyzer is I made up an attenuator chain. And what I've done is I have SMA attenuators. These are 30 dB each. And so I made 60 dB of attenuation, which is 1/1000th, I believe. And then I used my fancy, I have a connector kit that allows me to make up all the connectors to go from an N-type connector to SMA to RCA. BNC RCA. So I had to use my fancy connector kit to buffer my, or to isolate my transmitter from my receiver, or in other words, isolate my NTSC generator from the spectrum analyzer. So if you're about to hook your spectrum analyzer to something, think twice. Go ahead, think 3 times before you hook something up to it. So I wanted to show everybody that I had done that. All right, let's try and get you back on the main screen here. Somebody just asked if we're drinking. I don't know if they meant me or you. I'm not drinking.
No.
There you are.
So the manual, so I'm getting 565.
I am doing heroin, though. That's...
Are you?
No. I shouldn't say things like that, I suppose.
No, you should not. This is a teenage friendly show.
Okay.
Don't do drugs unless your doctor actually tells you a good reason to, for a specific one.
For that matter, stay in school.
I should have printed this out. I'm looking for on the manual early on where it says the DC output voltage. That's maintenance section. That's not what I want. AC output circuit. AC amplifier gain, DC, dB max.
So while you're doing that, let me show off a book I have. And this is a book that we'll talk about this probably later because it's the kind of book I know Ben likes also, is my National Applications Handbook, and this is from 1980. Let's see if we can get a good shot here. and it's so old that this flap was bent over, and if I bend it, I see the actual color that it used to be, the actual orange. I had thought they were yellow. My memory has faded in time. But this is the Linear Applications Handbook. And in here, let me make the screen bigger. Yeah, it's not going to do it. But in here, they AN31 is a collection of op-amp circuits, and this is what Ben and I go on about. Almost everything we've talked about with op-amps can be found in this old application book. So if you want to find out lots of, like, there's sine here's the sine, hang on, it's a Weinbridge sine wave oscillator right here, done with a light bulb, which is what we were talking about last week or the week before. So I just had to pull out this book to show it, based on that whole conversation of using a light bulb to generate a sine wave. They also show other sine wave generators in here. So this is a wonderful app note. Here's a differential input instrumentation amplifier. They get so I found this on TI.
That's right.
Go ahead.
TI, this led to the book that TI published from one of their applications gurus some years ago called Op Amps for Everyone, and they keep revising it too. So.
Well, that's why I was going to say when I originally went to AN31 in the TI, they've changed it. It's not, they don't even have the light bulb circuit in there, but they do a lot better job of describing the formulas for each one that's in there. So, yeah, this is how I learned analog, was by reading this book and the books that came with it from cover to cover until I understood as much as I could.
Right.
I don't want to say I understood everything, but I certainly gave it a shot.
Yeah, so I didn't find it in the manual, but I'd remembered, because I actually said this before. The DC output is meant to be a DC value that directly correlates to the meter position. So full scale at 1 or 0 dB is meant to be 1 volt DC. So they're not exactly agreeing. I would almost wager that the meter is more accurate than this, but again, that's where I have to try a few different things and make adjustments if I think this is off.
Right. Yeah, that'll be interesting to see how it stood the test of time there.
Yeah.
So, do you have your camera turned on still? I'm having trouble finding it.
No, you're looking at my desk camera. I'm waving at
right.
you.
Okay. I didn't know if you had a second one ready is still going somewhere else.
I can only send you one video.
Very good. Okay. I was making sure I wasn't missing it. And we're coming up to the top of the hour here.
Yeah. So I know I'd mentioned some other stuff too, but I've been playing with testing Rms. I got some.
Yeah, show us what else you got going there.
Well, this was because getting into all these discussions about retro computing with everyone inspired me to get some. Well, I needed to do this anyway for the Roland digital delays, but I wanted to buy some 4164s and 41256s DRAMs, but they came from AliExpress, as you might imagine, packaged like, this kind of way, with saran wrap in foam. Actually, the 41256s, I've put them in an anti-static bag since they arrived, but they were all just in a plastic bags, thermally sealed. Not even an anti-static bag, just a bag. And that was in a bubble wrap bag, and then it came from China like that. So I'm like, So far I've tested 2 of them and they were great, but I needed a way of testing them because I wasn't trusting the packaging, as you might imagine. So there's been a bunch of clever, helpful retro computer people out there who've done Arduino sketches for RAM testers. So far, that was the other one. If I look at COM7 here, so I've got this sketch going, and I'll share the screen.
Commodore SX64 man said, don't get the Micron one, MT ones. We used to have a lot of failures in the Commodore computers from Micron brand.
I didn't get those. I'm getting now you're getting the Skype screen because I wanted to share the whole monitor.
Yep.
But can you?
We'll get there.
You should be seeing. You should be seeing my browser and Arduino.
We got it. Yeah.
This is just reporting. So far, I've done like 16 iterations on this one chip, and it's passing everything. So that's good. And this will do 4164s and 41256s because it's just an extra address pin. So there's that. I'm going to modify the sketch though because I don't like how it just reports the serial only. I want it to just do some quick tests that are pass-fail and give me a red or yellow LED. Someone else did one that did that, so I'll probably try theirs and just adjust.
Now, is that bit banging? Somebody's asking how on earth is an Arduino fast enough for RAM testing? I assumed it was bit bang.
That's why it's not bit banging. If we look at the sketch here, they're actually using. They do identify the control pins and the data in and data out, but the reading and writing is using ports on the actual on the Atmega 328p. They're doing hard port, like this is lower level code.
Right. But there's not an external state machine or PAL that actually then runs RAS and CAS, right?
There's no need.
Are they doing?
Because the tests are all done within the refresh time period. And you'll see times here that are like 10 seconds, 12 seconds. That's because it runs the whole test.
Oh, it's not running it at speed. Yeah, that's a 1 microsecond cycle time, whereas DRAMs typically have access times of between 120 and 150 to 200 nanoseconds. So it's not running at full speed. If I can trust that comment where it says, is that milliamp or nanosecond? It looks like 9,000 nanoseconds.
That's the time it takes to run the entire test. Though,
okay.
Which is filling up the RAM, reading it all back, comparing everything. Like that takes a long time. And then doing that over and over and over with different patterns. So that is slow. But the actual like refresh is refresh. You're charging capacitors, right, Bill? So the capacitor will discharge no matter what you do, whether you access the RAM quickly or slowly. If you access it too slowly, then you're obviously dealing with that.
Right, you'll lose it, right.
Yeah, but refresh is not actually, with the way these tests are running, it's done fast enough. Each individual read and write sequence is done fast enough that the refresh doesn't come into play.
Right.
Though
as long as you read or write the entire chip within, I forget how many milliseconds, and you continue to do that, that's the same as refreshing. You just have to read every row within a certain number of milliseconds, something like 16 milliseconds or something.
That is what the testing is doing. So it would be, what I would like to do though is add to the sketch and give it a mode where I could have it prolong the read times until it starts reading errors and then get some idea of what the actual refresh time requirement is for that device. That just out of interest. So that was one of them.
So a big part of DRAM testing for us was the voltage you test at, because using 4.75 volts will simulate one kind of failure. It affects the speed. Or testing at 5.25 volts simulates another failure. So our DRAM tests actually would change the voltage to the device during the DRAM back in the day. I assume they still do something similar.
Right.
Also, then the testing, we would test for things like adjacent cell. There goes that squeak of the chair again. The adjacent cell. So you would put in a pattern and then read the pattern around it to make sure you haven't bled into the nearby cell. There's just a couple dozen failure mechanisms that we would test for back in the old DRAM days.
Right. So the other thing that I'd mentioned, I don't know if anyone's interested in this or not, but where was it? I put this HV EEPROM. This guy, and I hope he joins us someday, named Matt Millman. He has a blog and a bunch of projects, and he designed this. This is, and this is particularly relevant to me. Oh, wait, let me switch back to the camera. Oh, I am on the camera.
There we go. Yep. Ooh.
I'm on the camera. Oh, I'm still screen sharing too, am I?
Yeah, it's the forever ZIF socket. It looks cool.
Right, so
now, somebody mentioned some SDRAMs take seconds to start providing broken data. We got a brand of DRAMs in the old days, in the C128 days, where powering off for several seconds and turning it on, we would retain the data. And that sounds like not a useful feature. Well, we had tried to determine the difference between a cold boot and a warm boot and a hot boot by putting certain data in DRAMs, and we were running into the fact that we turn off the computer, turn it on, and we still had data it started acting like CMOS. So the retention time was something that we found could be seconds, you know, but you couldn't count on it. One bit would flip, you know, within a few hundred milliseconds, and then, but the rest might maintain for whole seconds.
Because there were so many vagaries of the semiconductor production process too.
Yeah, yeah.
Yeah, and
somebody called it a benception.
Yeah. Someone mentioned brand of RAMs. Yes, I didn't get microns. These, but who knows what these are? They look brand new, but they could be recycled. But these are branded as Philips. The MN part number is a Philips part number. But then again, It's got the M in the box, so I think that could be micron. So I don't know, right?
And then, I don't want to say that it used to be Mitsubishi used to have an MM number, but there was somebody had one.
Yeah, Mitsubishi do use the same prefix for some parts, and they also have M5N and ones like that, which I'll actually get to because I have some Mitsubishi retro microcontrollers to show you.
So just in case everybody missed it, we're not advocating wrapping your DRAMs in Saran wrap, unless it's ESD coded Saran wrap.
I doubt it. And I hate the way they package chips coming from China nowadays like this. But
this is from AliExpress, right? Where it's random packaging.
When you're trying to get something that's been used, and the only place you're getting it is selling it on AliExpress, you got to take what you're given and hope for the best, right? These all look pretty clean, but these are TI chips. Well, they're branded as TI chips. Again, who knows, really?
You're right.
Got to put my finger in front.
Yeah, back up a little, right?
Hey.
Yeah, it hates focusing on black. Yeah.
So you see the TI logo on that. So these are the TMS 4164s. 150. I think they're 150 nanosecond versions. I'll test some of those a bit later. So the other thing that really interested me too was those legacy microcontrollers, because I had a few, and I mentioned at the beginning of our stream today that I used to, back when I was fresh out of my associate's degree program in college, I was a service tech for a company that imported and serviced telephone typewriters for hearing impaired and deaf people in Australia. And those were mostly made here in the States by a company called Ultratech that I believe is still doing it. And they were also there were other versions made in Japan, and they all used 8039 microcontrollers. The 8039, a lot of people have completely forgotten about this family. The 8039 is the predecessor to the 8051. It was really the first serious microcontroller released to the market that had a CPU and I/O and memory control and
time of day also.
timer. It didn't have time of day. It had
Oh, TDD. I'm sorry, Chris.
it had timers in it, and then
Right,
it was
right.
multiple source. So I've got an NEC 8039 here. This will go at 11 megahertz. There's a Mitsubishi one. You mentioned Mitsubishi. They had the prefix on this M5L.
Okay.
That's a 8039P. That should go 11 megahertz as well. Some of them were a -6, which could only go 6 megahertz. And these had even at 11 megahertz, they had like a 550. It was like they divided the clock down, so it wasn't 11 megahertz. It was like 500 kilohertz machine cycle. Gosh, this is frustrating getting this to focus right.
There, yeah, it almost focused for a second. Yeah.
This is a Mitsubishi one.
There, that's good.
This is the P6, which means it was sold and marketed as a 6 megahertz, but it could probably go faster because this one's newer than the others, clearly. This one's actually a spare that was never used. It's never been used. But in the same family, they had the Intel. Also in the same family had the 8041s and 8040s and 8042s. This is an NEC 8041, which I pulled out of something or other. I don't know where it came from. And these are all part of the family called the MCS 48 because the main flagship microcontroller was called an 8048. And this guy recently, Matt Millman, designed this board to be able to read and program MCS 48 microcontrollers and other things, which is awesome. So I had to go build one. When I found it, I've got to do it because I've got this 8041 here. I'm curious what's inside of it because it's a factory mass programmed ROM. Most of the keyboards for IBM PC and AT, the keyboard controller was an 8042, which is another member of this same family. And there was one on the motherboard for the keyboard, the 5-pin DIN jack that we used to have for keyboards, if you remember those.
Right, right.
And there was also an 8042 inside the keyboard itself doing the key scanning and generating the key code,
Right,
sending it
right.
over serial. So I'm like, I'm just really curious. So I know that these modern, cheap, universal programmers don't support any of the old devices, which sucks.
Right.
You basically have to build your own thing like this with an Arduino. So to that end, what I found was Matt had written this simple Windows program, which I'll just share my screen again. Right, called
Right.
HV EEPROM program. He gives some source code for a DOS command line utility that does the same thing. It's already detected the right one. And these are the devices. So this will support some of the old ROMs that are used in some of the retro computing devices, 1702, 8702, 2704, 2708, some Motorola, 68764 and 68766. I guess those are microcontrollers, but I'm not sure. The whole MCS 48 family will be done by this software. And then for factory mass programmed variants, I can just read them. But 8041 and 8042 are not in here. It's got 8741 and 8742, which are the UV erasable EPROM versions. But we'll see. So I've got this. This is an 8041, so it's factory mass programmed. So I'll choose 8741 and just do a read because it's not going to it's not going to be it's not going to be blank, I'm sure. But here's the thing: sometimes those factory mass microcontrollers, they would do a run for some customer and then they wouldn't use them all, so they'd
Right.
sell them as the you could sell them and use them in place of the ROM-less version and just have the EA pin pulled high, so you have a separate ROM chip for it. So this is warning me I've got a
cool,
slightly saggy power supply. So this is really well-written little software that Matt did. I'm impressed, but I'm going to continue anyway because I'm not too worried about it. And it says it's not blank. It's found data at the first byte. That's the other nice thing. These old microcontrollers had no security.
Right, right.
So we have this luxury of being able to read from them. So if I read from device, and this has 1K byte, because I guess the 8041 was a 1K version, the 8042 was the 2K version. Save that as a binary file, and I've done this already before, but let's go. This is mystery UPD 8041 AHC ROM read as 8741. I'll save that binary file. I've already done this before, you can see, so I'll just override it. And then in my XG Pro, the EPROM programmer software has a nice hex view, so I like to use it.
Yeah, right, right.
The program is not plugged in right now, but let's go and load. Yeah, we'll load that file. It's going to be a binary file. Here it is. And 1K, and it's just giving me what looks like
a test pattern.
It's just counting up the addresses. So to me, that doesn't look right. And it read up to 7F, which is 37F, which is the last byte. Actually,
right,
no,
it read 7F from 7F.
3FF. Right, so that doesn't quite look right to me. So maybe I've done something wrong, or maybe this legitimately is inside this factory mask ROM version, because I don't know where I picked up this part. I pulled it off of something. So I'm going to try something else just for fun. I was going to say that almost looks like a test pattern, but then I realized it starts at 0 and not starts at 3, 1. Counting up. I'm going to read it as a generic 8048.
All right.
I wonder if I can configure this. This is for different devices. Maybe there's some, Oh, these are just writing options, so I'm not going to do that for verification. Don't need to change that. So I'll read it as an 8048. Read from device. Yes. So I've read that a kilobyte. Save as bin. And this one's read as 8048. And again, I've done this before, but I'll just replace the file. And then in XG Pro, I'll load the new one. And here, this looks more like actual code.
It does. Look at that. You got actual ASCII.
Bunch of zeros here and there, but that's just spacing between routines.
No, scroll up and look in the right. You'll see some actual ASCII. Yeah. I saw some ASCII code in there.
And that's how you know.
It was a message.
When you've read it.
There it is. Look at the bottom.
Epson. This is programmed by Shinhwa Digital.
That's what I was looking for. Yeah.
So I don't know where this came from, but probably out of a keyboard. I'm thinking I pulled this out of an old IBM compatible keyboard from somewhere back in the dark days. But there it is. That's actual code. So from here, I can use a disassembler and start labeling things and working out where things are located in different memory sections. And yeah, what fun.
Cool.
But the goal there, the reason why I wanted this to work, and I've been able to test it, I'm happy I've been able to test it with this 8041 chip and know that it works, is because when the time comes for me to get the it's an 8048 in the Roland delay rack, the SD3000, I'll be able to get the code out of that I shouldn't say this publicly because Roland might get mad at me, but hey, give me a break, guys. The unit's like 35 or more years
Right.
out of date and old, and it's becoming a collector's item, and people need to be able to preserve these things. They spend money on new gear. Don't worry, I've got a lot of new gear. So that's
very cool.
That's the starting of the fun process. So I guess coming up here soon, I'll be documenting some of this, and I already have a few different disassemblers for 8051 and 8048 that I've played with over the years, but I hear that MAME is the way to go for these things now.
And what is that?
MAME is
we lost you. Well, we got almost all the way through. You can tell Ben's got a much better internet connection these days than when we first started. Same as Sakosha. I don't have my glasses. Sakosha for Commodore MPS printers. So I'm reading from the chat box. So not sure if Ben is coming back or not. Let's check, see what's going on in Skype. He may have a serious issue over there.
Hey,
and there he is. Excellent.
I don't know what the hell happened there. I was trying to switch cameras and I ended the call somehow. Sorry.
Right.
Yeah, MAME is it's a suite of reverse engineering or code decompiling tools for preserving old computer games. That's my understanding. It may have other original purposes, but that's what I understand it's used for.
Mr. Landfill just said almost that exact same thing in the comments, so must be it.
But the nice thing about it is people have had disassembly capabilities. It's kind of modular and table-based, so it's been really easy for people to add new instruction sets or add, I should say, old instruction sets for a lot of different processor families, and MAME can basically do them all. So MAME will do the NEC UPD 78K series like these, which is also used in some of the old synthesizers and audio gear. I don't know if it does 8048, but I bet it does. Because 8048s, MCS 48s were also used in a lot of pinball machines.
Okay. So yeah, Tosca in the chat channel said Roland men in black sunglasses got to Ben while you were gone. It was the Roland police was why you disappeared there for a bit.
It's like they busted down my door and took me out.
Oh, they were quick too. Yeah, I mean it's Roland. Well, you expect nothing less.
They're ninjas.
Yes.
So.
Wow, thank you for the tour of that. That was very cool, especially to see the ASCII pop up. That's when you know you're on to something, when you actually see the code that's in the either as comments or in the executable itself where it's using ASCII.
Yep. It's a lot of fun.
So cool. All right. Well, I want to thank everybody for coming this week. I want to remind everybody about Coriolis-Effect. The website of Coriolis-effect.com. You will see our past videos. You will also see a Discord invite there. Join us on Discord where we talk about this during the week, and we can post lots of things, intermediate results as we get them and stuff. Follow Ben as he does this, some of these retro projects here.
Yep. Cool.
So very good.
Thanks
well, it's good seeing you, Ben. Yeah,
You too.
And we will see everybody here next